Hello everyone. Today we are presenting our presentation on the topic cooling of a copper sphere. Its aim is to understand cooling process using data modeling and mathematical modeling. To understand the problem statement, a copper sphere is heated to 100 degrees Celsius by letting it sit in boiling water at time t is equal to 0. The sphere is placed in a tank where water of the constant temperature 30 degrees Celsius is flowing past it. The surface temperature T of the sphere is measured with small but accurate thermometer soldered on the sphere. The temperature for the first 12 whole minutes is recorded in the given table. Use the data and construct at least two different models describing cooling of the copper sphere, making some suitable errors estimation to try to evaluate models. Discuss similarities and difference of your models. What is the basis for the difference? So the theoretical background is as follows. Cooling concept. When a hot body is placed in a cooler environment, it loses heat. Rate of cooling depends on temperature difference between body and surroundings, surface area and material properties, medium of cooling, air, water, etc. Newton's law of cooling, the statement is as the rate of change of temperature of a body is directly proportional to the temperature difference between the body and its surrounding. Relevance to our experiment is copper sphere initially at 100 degrees Celsius, environment at 30 degrees Celsius, and is expected to follow exponential cooling. Our data will be checked against this theory. In mathematical form, it can be formed as dt upon dt is equals to minus k t minus t of environment. Okay. And by solving, we get an exponential concept. Tt is equals to T environment plus T naught plus T. The graph here shows the cooling of copper sphere, which is across exponential data and time taken. The blue line with dots shows the actual recorded temperature. The red dashed line is the constant environment temperature of 30 degrees Celsius. So we can notice here that exponential decay shape, the cooling is fast at first and then slows as the sphere reduces the temperature according to the surrounding.
So here is the experimental setup. Copper heated at 100 degrees Celsius in boiling water, placed in flowing water uh, with the temperature of 30 degree from the environment. Temperature measures uses a small accurately thermometer, then data collected. Here is the data collected. Temperature recorded in first 12 minutes, at later in 15, 20, 25, 30 and 60 minutes. Shown in given table T1 uh, temperature versus time. Then we observe the study of that object of the study, construct the all latest least values and the least two numbers model for cooling from the copper sphere. Essential errors, compare models, discuss difference, and determine the time with the sphere reaches at 31 degrees Celsius. Orange sphere, here is the one photograph. Here we see the cooling experimental setup. Their orange sphere is heated, uh, that is a heated copper sphere. It is up to 100 degrees Celsius. Blue container, it is a water. When we take bath, it is up to 30 degrees Celsius. Next slide. Parametric in our case, essential temperature is a water we take to bath, it is 30 degree. Cooling conditions and essential data. Fitting the data follows the exponentially delay curve, uh, can be calculated using 2 points. Key objects matches well and experimental cooling behaviors. Explain why cooling slow and spherical approach 30 degree. Methodology. We first apply Newton's law to cooling, which predicts the exponential decreasing in temperature. In our experiment, the environment is the 30 degrees Celsius and the sphere started at 100 degrees Celsius. and the cooling condition determine the rate of the coolings. When we plot the model, to close follows the experimental data, confirm that a spare coolings is exponentially, but we can check it accurately. It compares with the model and then approximately. Next slide. Here is the we use the formulas like T small t in the temperature of the object at the time small t. T is the ambient temperature 30 degrees Celsius. T naught is the essential temperature. It is up to 100 degrees Celsius. K is a cooling condition and constant. To construct the model, we have to use this given data and points to find the value of K. For example, using the data point at T, all T is 1 minute and temperature 1 is equals to 88.1 degrees Celsius. Therefore, 88.1 degree is equals to 30 plus 100 minus 330 e raised to minus k into 1. And here the answer 58.1 is equal to 70 into e raised to minus k.
So, hello everyone, myself Mandar. So, next step of our calculation part is error estimation and model evaluation. To evaluate the models, to calculate the predicted temperature using the derived model and compare them to the actual measured temperature in table 4.1. The difference between the predicted and the actual values represented the errors. So calculate the mean absolute error MAE or a root mean squared error RMSE for more robust error estimated. So our next slide is depend on similarities and difference of a model. So similarities are both models aim to describe the cooling process and predict the future of temperatures. So in its difference is an exponential model like Newton's law of cooling is based on physical principles, while a polynomial model is purely mathematical fit to data. So the exponential model might be more accurate for predicting long-term behavior, while polynomial might fit initial data points for more closely but diverge later. So our fourth point is basis for differences. So, so the differences arises from the underlying assumption and the mathematical forms of a model. So Newton's law of cooling assumes a constant rate of heat transfer proportional to temperature. So while a polynomial fit simply aims to find that best approximates the given without necessary reflection and physical processes. The fifth point is based on time when temperature reach 31 degrees Celsius. So it's a using the exponential model which is derived in a fourth slide. So our basic formula is derived. Uh, Capital T is a temperature and small t is a time. So 30 plus 70 into e raised to minus 0.186 into t. It is our mathematical model. So if we put the all values in it, so we get T is equal to 22.84 minutes. So our basically final answer is the time when the surface temperature reaches at 31 degrees Celsius is approximately 22.84 minutes based on exponential cooling derived from a Newton's law of cooling. So that's all about our presentation.
Thank you.
Thank you for watching.